Today we're looking to go beyond basic triangle proofs and now conclude some things about other parts of the triangle that we hadn't mentioned before. And in addition to that, we're going to talk about circles and how do they fit in these proofs. Our first concept is called CPCTC, and it says if two triangles are congruent, then any pair of corresponding parts are congruent, whether they be segments or angles. The abbreviation we're going to use for this concept is CPCTC, but you have to know what it stands for. Corresponding parts of congruent triangles are congruent. To use this, you have to have triangles congruent first, and then you can start picking out the corresponding parts. That's why naming was so important in the last section. We had to make sure that our correspondence was there. So a quick example. First thing we're going to look at is that we have two given triangles that are congruent, triangle ABC and triangle DEF, and we want to name all pairs of congruent sides and all pairs of congruent angles. So I'm going to grab my highlighter here, I'm going to highlight A and D, and on the diagram I'm going to do the same thing. And then let's go with B and E in green. And let's go with C and F in pink or magenta or whatever color that is. So it says we want to name all pairs of corresponding or congruent sides and congruent angles. Now if the triangles are congruent, then by CPCTC all the pieces that are corresponding are congruent. So I can start with the angles. Angles are going to be really easy actually. Looking at the diagram, the orange angles are angle A and angle D. Looking at the green angles, angle B congruent to angle E, and then the pink C congruent to F. And that's the easy part. The more challenging part is, what about the segments? So if we start at this orange angle and went our way to the green angle, we'd have AB. So I know AB is one of my sides. And looking on the other side, DE, because we went from A to B, D to E, orange to green. Instead of going to green, maybe I started with the orange and went to the purple, or pink, sorry. AC, congruent. On the other side, the orange to pink is DF. And then if we started at green and went towards pink, we'd have BC. And that's congruent to EF. And we can also figure this out in the naming. AB are the first and second letter, same thing with DE. AC are the first and third, DF first and third. BC second and third, EF second and third. So without the triangles, you can name these just by looking at the names of the triangle. So how does this fit into a proof? So we're started off with TB bisects angle ATS, and then we also know that TA is congruent to TS. I'm going to mark off everything I know for sure in green. And that's it. Then I'm going to start marking off what I could potentially get in red. So TB bisects angle ATS. So I've got a bisector. That means it's going to break it down into two congruent parts. So ATS is the angle that's being broken down. So I'm going to say that these are congruent. And then looks like a triangle. I'm really close to getting everything I need, except I either need another angle. And it's going to be tough to get angle S congruent to angle A at this point, or I need another side. Oh, TB is congruent to itself by the reflexive property. Now from there I can prove that the triangles are congruent, and then start picking out the pieces that I need. The pieces that I need are angle A and angle S. And you'll notice that the things I'm ending up with, I'm marking that off in blue. My intermediate steps I'm marking off in red. And the stuff I'm given directly I'm marking off in green. That way I know this is given information and I'm good to go on those. Alright, so given information, we're going to not write that down. You guys know how to do that. So we set up our statements and our reasons. So we know that TA and TS is congruent. That was given to us. Now the red steps are the ones we went a little bit past that. So in step 2, I'm going to say that angle ATB is congruent to angle STB. And that's because an angle bisector creates two congruent angles. From there, I said that we had TB congruent to itself. And anytime we say something's congruent to itself, that's a reflexive property. Step 4, now the triangles are congruent, so I'm going to go with the same naming that I did here in 2, because I want to be consistent. I don't want to guess. I'm going to make sure that I'm correct on my naming. So ATB congruent to STB. The triangles are congruent. And we said it's because we had a side, an angle, and then a side. That's SAS. From there, we're to our proof statement, A congruent to S. Corresponding parts of congruent triangles are congruent. The congruent triangles were these two here, ATB and STB. The corresponding parts are angle A and angle S, so they must be congruent. That's the idea of CPCTC. I want to get into the circle stuff, so we'll skip that previous one there. Circles. So we have circle O is pictured below, and O is the center of the circle. That's really the most important point of the circle. It's really critical that we know where the center is. Two segments that come from the center and go to the edge are OA and OB. Those are called radii of a circle. Plural, or that's the plural of radius. So a radius is a segment that goes from the center of the circle to the edge, to any point on the edge. And we're going to pretend that A actually stops there on the circle. So the important thing for proofs in this section is that all radii of a circle are congruent. So if you have a circle, any radius you can draw in that circle has to be the same as any other that you can draw. Within that, we also have two formulas that are going to be used throughout the rest of the year, really. Circumference is 2 pi r. That's like perimeter, so it's if you were to walk around the circle. There is another formula you could use for this called pi d. And then the area of the circle is pi r squared. So you're going to take your radius, you're going to square it, and you're going to multiply it by pi. And we're going to use the pi button on our calculator when we do these questions. Alright, so let's get into an example with circumference and area, and then we'll look at how they apply in proofs. So we are finding the circumference and area of a circle if the radius is 10. In this case, it says to round our answers to the nearest tenth, so we don't want exact answers. So my formulas are this: C equals 2 pi r So then I know my circumference is 20 pi, and I'll find out what that is in actual decimal in just a minute. But I want to set up the next part, which is the area. So to find out what those decimals are, we're going to do 20 and then find the pi button on your calculator. Don't use 3.14 because that will affect your answers. So rounding to the nearest tenth is 1 decimal place, and I get 62.8 for the circumference. For the area, I'm going to take 100 times pi, and I get 314.2. Okay, don't round unless it says to, though. If it just said find the area and circumference, you'd want to leave your answers as 20 pi and 100 pi. So how do circles apply to a proof? So the first thing that should be a dead giveaway is this information right here, circle A. Again, just like we did before, anything that's directly given, I know immediately it's true. I'm going to mark that off in green. That's direct givens. ME congruent to DE. I'm going to think about this circle and what does that tell me? So we just said in a circle that all the radii are congruent. So if it's circle A, that means the center is at A. Any segment I draw from A to the edge of the circle has to be congruent to any other. So I know that AE, AM, and AD are all congruent. So if you look at my triangles now, my triangle MAE and triangle DAE, I actually have 3 pairs of sides congruent in both of them. So my next step then is to take that information and turn it into a proof and show that angle MAE and DAE are the same. So as usual, we're not going to write our givens down here because you know how to do that. But we'll get to the next step. We'll get to the radii. Now you don't need to state that the radii in a circle. I can see that in the diagram. We're going to say that AM is congruent to AE, which is congruent to AD. And my reason is going to say all radii of a circle are congruent. So when you're given, if you see the little circle with a dot in it, that's telling you this is a circle and this is what the center is. So based on the given information and what I just marked off, I know that the triangles are congruent. So my next step will be triangle MAE congruent to triangle DAE. Side, side, side. And what I really love about CPCTC proofs is a lot of times if you're looking for an angle, they're telling you what triangles you need to prove congruent. So we proved the triangle's congruent. Let's pick out the corresponding parts. And I know for sure 100% that they match up because I just named them to make sure that they did. MAE congruent to angle DAE. CPCTC. Once again, you see a circle, you know all radii of a circle are congruent. It's very likely you're going to be using that in a proof.